I teach a class. My favorite class is on communicating data and statistics. It's everybody's favorite class who takes it. I think there's some selection bias, though, because maybe only 40 people will show up to the class, even though there are thousands of people at Columbia who should take it. But there's more selection bias because out of 40, maybe I'll end up with 15. And they're great, those 15 people. And one thing I tell them is that like everyone who's a statistician is a teacher. So I teach people, we're teaching how to communicate, how to teach. You all know the most important person you need to communicate with is yourself 6 months ago, and she doesn't answer emails. We're all teachers. So I think you all, like, this is not a room full of professors, but I think anyone who's worked in any kind of data analytic capacity will recognize that that might even be most of your job, is to explain what you're doing to other people, to teach people, to reassure people, to tell them, no, I'm not going to jump all over you, what you're doing is okay, so forth. And it's funny because teaching, it's just my job. It's nothing I've ever been trained to do at all, which is probably true for all of you. Now, when I learned a lot as a student. My first semester in graduate school, I was one of 3 teaching assistants for Fred Mosteller, who had been teaching introductory statistics at Harvard for 30 years, had written many books. He took us to lunch every week, and I remember once he asked us our opinion on some, I can't remember, some education thing, like what should be done, blah, blah, blah. We each gave our opinions, and then he just snapped right back at us. He said, that's not what you should do. I said, what do you mean? And he said, when somebody asks you what you think, it's not because they care what your opinion is. They're asking you as a statistician. So you should answer by suggesting how you would design a survey or an experiment to study it. That's why they're asking you. Well, maybe we could say more things, like maybe you could design a measurement error model or whatever, but the same principle. Now, the other thing he told us was that you never know what people are going to get out of your class. So he said he would teach different things in different years, and sometimes he would run into a student years later, and it turns out they didn't get anything out of his class except one throwaway remark, and it changed their life. So you don't know what it's going to be. So when I teach, I always say I need a take-home message in every class. So every class, like, what are we going to do today? This is what we're doing today, and you're going to get something out of it and come home with this message. And so I thought, I have to do that for you. You came, you paid Jared your hard-earned money to hear this. You're not here just to be entertained. You want to learn something useful. So what could it be? Well, like R tips. Maybe not. You all know more about R than I do. There's a graph here. I guess I can draw it here. So the x-axis is what's the x-axis? What's the x-axis always? Time, right. The x-axis is time. The y-axis is like how good you are. And then it's like how good you are at R. And here I am, gradually improved. Well, I started using S, but same idea. So I gradually improved. Now, here you are. I've been improving, right? Here you are who started 20 or 30 years after me, and you're up here, right? So for me to say, hey, look what I learned just now. This is stuff like, hey, I learned a new trick in base graphics. You want to hear it? I mean, what next? What do you want? Like Space Invaders cheat codes? It's really not going to happen. So I can't do that. Well, I could tell you about Stan, but I think maybe that's too wonderful to waste on you right now. Maybe next year, Jared, if you invite me back. So here it is. I'll tell you something that you can take home. You can take to the bank and succeed with it. It's this thing you might not have heard of. It's called p-values. And what you do is you run an experiment. Now, it's kind of important that you do an actual randomized experiment or a random sample survey, something with probability in it, because there's a well-known principle in applied statistics that a chain is as strong as its strongest link. Right, you see, yeah, exactly. You have to think that one through, then you laugh, right? attempt. It's not really true that the train, but this is how people act. So the idea is you need that identification. That's your key to the kingdom. And then once you're inside the castle, you can ransack the place, right? So run an experiment, okay? Then you have a pile of results. So for every result you have, calculate a p-value. If it's less than 0.05, you've found something real. You've made a discovery. And if it's more than 0.05, then you've proved that something is 0. And so either way, there's a win, but you can get a little bit more out of this. There's another little trick you can do, which is if the p-value is like between 0.05 and 0.1, you can say that you've discovered that it's a small effect. And then you can get entire patterns out of this. Now, you might worry if you do that, you might worry that your measurements might be too noisy, that these things might not replicate, but don't worry. Okay, don't worry, because what do we care about? We care about two things in life, right? Only two things in life, for reals. Bias and variance, right? And so, but I mean that. I mean that. I don't necessarily mean it the way people always mean it, but I mean it. Now, you don't have any bias because you remember you did a randomized experiment, so therefore you have no bias. You also have variance. Well, the problem with variance is if it's too big, but why is it a problem if variance is too big? Because that means your power will be too low. Why is it a problem that your power is too low, that you won't get statistical significance? Luckily, you've followed my advice and you've looked at enough things that you've found statistical significance. Therefore, retroactively, your power was just fine, right? This is, this is what we're going to say, like, in a couple weeks, right? The Warriors didn't need Kevin Durant. They whatever it is, right? Okay, the power is just fine. So therefore, your measurements were good enough. So you don't have to worry about that. Okay. Now, you maybe think I'm speaking ironically, and you might say this might work in academia, because the goal in academia is to publish a paper. Okay, so it's a little like academia is like sports, right? You want to win the game. Once you get the W and one more in the W column, the game is over. It doesn't matter if you deflated the football, whatever it is, right? I'm sorry about that. It's just that Jared told me I had to mix in sports analogies because Jared gave me this whole pep talk beforehand, about how to speak for this audience, and he was saying, statistics is traditionally full of sports analogies, and he was thinking, it's really become a little too soft, a little bit too touchy-feely, and so Jared's reintroduce the bro element into your talk. And I said, Jared, if that's what you want, I think I am not the right speaker for you, but whatever. So I'm trying my best to throw these things in, if you will. So the point being, though, is that in academia, it's you just want to win once you win the game, it's over. In in real life, you all mostly work in the real world, right? Whatever that means. And there it's more like a game of ping pong, you want to keep scoring points. And ping pong, Jared? I don't know. It looked better in the slides. He wouldn't let me use slides either. That was another thing. So, okay, so you might, it's a little different because your goal, in business, is to make money. Maybe you're not all in business. Your goal in government is to help people out. Often it's to help people use the services available to them. And nonprofits, you might be working in medicine. You really want to change things for the better. It's not just ratcheting up wins. It's not just about having a fancy CV. It's about things that are going to count to somebody, to real stakeholders. But But it actually, this trick I told you about the statistical significance, it kind of still works in the real world. And I've seen that. Like, I've talked to people, like they're doing A/B testing, and they're like, yeah, we set the threshold down to 0.8 instead of 0.95 because we wanted to get this. Like, people are, you can use these tools to succeed. It's kind of cool because it's like alchemy. You've like converted randomness into certainty. But there's a principle we sometimes call it the conservation of variance, which is that the variance has to appear somewhere else, right? So the flip side of taking something uncertain and pretending it's certain is that it will fail to replicate later, right? It's like the variance has to go somewhere. And that's why you could say a lot of statistics is like a pyramid scheme, and like you really want to get in on the ground floor, which I've never really understood that, because in a pyramid you want to be on the top because the ground floor is where all the suckers are, but they build the pyramid starting from the bottom. So I don't really understand the pyramid scheme principle. It seems to be just a terrible analogy. Okay, so how can we understand this? There is a tool that we can use. There's a set of tools, like you could use Python, whatever, but I'll say R, because this is the R conference. I spoke at the Python conference like a year or two ago, and I told them I didn't have any Python, so like, is that okay? And they're like, sure, it's just called the Python conference. It's not really. So I think this is probably similar. So how do we understand this? What we have to do is we have to simulate the world, and I'm serious about this. So if I want to, I mean, this is kind of old school, like you'd say, oh yeah, some thick-headed person doesn't understand the Monty Hall problem, so let's do a simulation. Like, who cares about the Monty Hall? I don't like the Monty Hall problem, actually, because I feel like it sends the message that probability is so tricky by giving, it's not really that tricky. You can kind of brute force things. But if you want to understand something like what happens if you call things statistically significant and then act as they're true and then do replications, what you want to do is simulate a world in which people behave in a certain way and then see what happens. And you can see what happens. So if you're working in your company doing A/B testing and you want to use an 80% threshold or whatever, the answer is not 80%. Like, to say that the answer is 80%, I mean, that would be like saying, like I'm a biologist and I want to grow a colony of like amoebas, and I give them like a certain amount. I give them like 2 grams of amoeba food a day, and like the answer to, like I said, then the question is like, how many amoebas are there in 3 days? The answer is not 2 grams of amoeba feed. That's the input, right? So similarly, if you want to know how reliable are your inferences if you do significance testing with an 80% threshold, the answer is not 80%. 80% is the equivalent of 2 grams of amoeba food a day. That's the input, right? The only way you're going to know the output is to run the simulation. So you can do that. Now, it turns out running a simulation is hard. So it's a lot harder, it's a lot easier to analyze data than to simulate fake data. And even in statistics, there's this funny thing, they talk about the likelihood. The likelihood is derivable from the data distribution, but the data distribution is more complicated than the likelihood. One likelihood could map to many data distributions. So it's easier to do Bayesian inference or just about anything else than to simulate fake data. But only by simulating fake data, or obviously sometimes you can do it through math, but that's rare, right? So only through simulating. You're like laughing, and that wasn't a joke. Like I got you all on the edge here. I could say anything at this point. So to simulate the fake data, you have to simulate a system. What does that mean if you're doing your A/B testing or whatever you're doing? You're working for the government and you're trying to improve people's use of social services or whatever you're aiming for. You have to have a model for the world. So you have to say, if I'm doing the A/B testing, well, how big is the effect that I'm testing? Okay, well, what's going to happen? Statistics is said to be the science of defaults. okay? So the difference between, say, a statistician and, I don't know, like, there are physicists who work on probability, and what they'll do is spend 10 years working on one problem, a really hard problem, building a lot of scaffolding. I mean, they're building the Chrysler building, as it were. Like that's a career. Statisticians, we're more like the guy who made Levittown, like, except without the racial exclusion and all that, where we want to build a lot of tract houses, you know, that's kind of how we think, okay? So you have to imagine someone is going to do this procedure, what was it, solve all your statistics problems using p-values. I think that was that Jared gave me that title and said, go from there. So this is really all just up to his fault. So he's like, you can't get out of this one. I guess I can. Yeah, try to tell you this time, you can't trap me. So it's not just, okay, how big is this effect that I'm studying? You need to have a hypothesis about that. And that's, this is really hard. What's my prior for the effect? I don't know. If I had a good prior for the effect, I wouldn't need to do the damn A/B test in the first place, you fool. Like, you can't think of it that way, okay? The prior is real, okay? The prior is real. I'm like one of those, holy rollers, like I feel God, whatever. I feel the prior. It means something. It's the distribution of actual effects. So you have to say, like, okay, all of statistics is about repetition. It's about the frequency. We're all frequentists here, okay? So the idea, really. So the idea is there is a stream of problems you're working on. You didn't get hired to do one A/B test. There's not one program you're rolling out. There's not one drug you're testing. There's a stream of these things. Now, in a usual talk, I would start saying, okay, what's our prior for this? How do you validate this? A lot of interesting stuff, like all our research, everything we do, like when we're not doing all the other stuff that we're doing. And when but here I'm framing it another way. I'm talking about how I want to help you, right? So you are you're writing an R program, a simulation. A little part of that little function in there, little thing is how you're going to analyze the data. But the hard part's creating the data. So you have a stream of problems coming in. Model that. It's not one problem, okay? It's not whatever I said, 2 grams of amoeba feed a day, right? You have a stream of problems. How large are these effects? To what extent are the effect sizes gradually going down? You got to model that. Now you put that in, it could be wrong, that's fine, then you go back and change it. But you got to make some assumptions about that. How fast are decisions coming in? When you make a decision, how long does it persist before you're going to redo it anyway? What are the costs? You kind of work it through. Then you say, here are a bunch of strategies. I'm going to follow the 80% strategy, the 95% strategy, the Bayesian strategy, whatever. Okay. Well, the way the Bayesian strategy works is it's optimal if the assumptions are correct and you average over the prior distribution. Of course, you don't know that, so then you'd have to try other models. That's fine. But you do that. Then you'll find out what will happen if you follow these strategies, if you follow a statistical significance strategy and act like you're sure. Okay. Maybe not so horrible. It's not necessarily so bad. I mean, you making decisions based on random numbers. Like there are worse things to do, like maybe not doing anything at all. That could be worse. So like you have to evaluate these things. It's not enough to say like, ha, you're doing it wrong, p-value, ha, that's so stupid. It might be fine, right? You need to simulate the fake world. That's the only way you can do it. So as the saying goes, to know the past, one must first know the future. All right? And so the great Raymond Smullyan said that. So you know this because there's this field called experimental design. And when you learn statistics or data science, whatever, you first learn. Now, I'm on record as saying statistics is the least important part of data science, which I think is kind of correct. That's another story. I mean that, actually. So you learn you data analysis first, right? And then you learn design. Or probably you never learned design, because they don't usually teach that. So it's kind of funny. Design comes first. You'd think you'd learn it first. But you can't really do a design unless you know how you're going to analyze the data. Right? You just can't. And I mean, you can make stuff up. But so, all of this is why I now refuse to collect data until I've first simulated fake data. I think it's kind of immoral to do it. Like it's like buying a product and you don't have a plan of how to dispose of the waste, sort of. Not quite, but it turns out it's a lot of work. So I'm actually involved in a project with a colleague I really respect a lot, and we've been stalled for like a year because I haven't simulated the fake data. Now, obviously, it's not my highest priority, or I would have done it. But the point is, I mean that. Like, I don't think you should anymore do that. It's very easy to just, now, sometimes the data are already coming in, but in that case, I feel like you should allocate 10% of your effort to simulating the fake data and so forth. That's my recommendation. So I wanted to tell you a couple stories about how I feel that multi-level modeling, I feel, is a way of life, a way of thinking about the world, partial pooling. Okay. So first I'll tell you the stories of increasing length. First, a very short story. When I was teaching statistical consulting many years ago, and the students were doing the consulting, and then they would come in and meet with each other and the instructor, and we would talk about the problem. So some student came in and said there was a problem. It was some company doing research in Silicon Valley, some like production of chips or something like that, and they had data on 21 plants, like factories, and they were fitting the client had come in, wanted to fit a regression model, and they had 16 predictors and 21 data points. So yeah, their reaction were like this, but then another student said, hey, I took this class last semester. He came in last semester, and he had 15 data points and 16 predictors. And I told him, come back when you have more data. And everyone's, okay. Well, wait a second. Can you really learn nothing? I mean, that's kind of like, what if I said you had 21? Did I tell this story in a previous? Okay, I can't remember. What if I had 21 data points and one predictor? Well, that would be okay, right? I mean, you still have issues where the data came from. That would be okay. So all of a sudden, 21 data points and 16 predictors. That's bad. I have too many. Like, I wish I only had one predictor instead of 16. How could more be worse like that? That makes no sense. So we had to kind of talk about it a little bit. So you realize you can actually learn something with 21 data points and 16 predictors. Well, maybe not by running them all in a least squares regression or even a regularized regression. But for one thing, you can make a scatter plot of each outcome against one predictor at a time. And then it turns out that no single predictor predicts the outcome. Well, you didn't know that before, right? So you've learned something. There's things you can do, right? Now, we're more familiar with this now, like people do genetics. They have lots of predictors. But like, there's something funny going on about that story. But like our reaction, how our instinctive reaction is so wrong. So second was a problem. This was the 4 treatments, 5 dishes, and 6 cultures problem. So this was another one from that consulting class. They say that you learn by teaching, right? And it's true. That there was a biologist, and they were doing something on little critters that were living in little cultures on dishes. And they were, I don't remember what it was, but there were 4 different treatments. And each treatment was being applied to 5 dishes. So there were 4 treatments, each one applied to 5 dishes, and within each dish were 6 little cultures. And they had 2 possible analyses, and they wanted to figure out which to do. So the first analysis was, so just to get this clear, there are 4 treatments, each one had 30 data points. So the first analysis is to say, take the average of all 30, basically treat them as 30 independent data points. You have 4, so it's a problem, you have 4 treatments, each one has 30 data points, take the mean, the standard deviation, go from there. But then it's like, well, they're kind of clustered on dishes, so maybe what we should do is take for each dish, take the average. And so then you only have 5 data points for each dish. Use that, like take the mean of those 5 and the standard deviation of those 5 as your data point. But then, so then that seems sort of safer to do the 5, right? I mean, it's not a trick. Like, it seems safer to do the 5. But then, what if I told you that it didn't really matter much, like the dish, there were no dish effects, they weren't interfering with each other in the dishes. Then I should really do the 30, because it's 6 times more information. So they were really kind of not sure what to do. Like, they really wanted to do the 30, but they were really afraid of doing the wrong thing. And so they were kind of stuck. So it turns out in that case, well, you can talk about with your neighbor for 30 seconds. What would you do? Talk about your neighbor, 30 seconds. Come on. What would you do? What? No. Yeah, sure, I'll take it. Okay. Okay. So, yeah, what to do? It's like, well, oh, it depends on the day. Okay, it turns out there's a right answer here, and the right answer is to do the 5, not the 30. And the reason is that it's true that when you do the 5, you only have 5, but so it seems like your standard error will be a lot higher. But remember, when you do the 5, it's the standard error of the 5 averages. And if you think about it, each one is an average. So if it's truly independent within dishes, the average of those 5 already has a 1 over square root of, the average of the 6 things within a dish already has like a 1 over square root of 6 inside of it because it's an average. And so it turns out that if there are dish effects, you of course want to do the 5, not the 30. But if there are no dish effects, then the 5 really just reproduces the 30. Now, not completely. There's some issues of degrees of freedom, of estimating variance. But pretty much, that's the right answer. So it's kind of interesting. A little bit of mathematical theory can help us out. So that's one example. Now, I'll tell you another example. Then I'm going to loop back, talk about why multi-level modeling is so great. Then I'm going to talk about the pluralist dilemma. I'm going to ask, why does it all matter? And I'll tell you why it all matters. I'll tell you a funny little thing, and then I'll conclude the talk. So the next story is, did I tell them about the chick brains? Did we do that last time? Not done? We haven't? Oh, OK. So in the 1980s, some epidemiologists discovered that kids who live near electric power lines were at elevated risk for leukemia. And so there's a question of how this could be. And because electric power lines, they do emit radiation. They're alternating current. Thomas Edison said they were dangerous, et cetera. But it's low energy. It's too low energy to ionize your cells and give you cancer. It's not even like microwaves that can cook you. It's less than that. So there was a theory if they could affect you at all, it could affect you through brain functioning. So your brain actually communicates like with itself with these, you've maybe seen these brain waves, like roughly 60 hertz cycles. There's actual like electrical action in your brain. So the theory was perhaps it would inhibit your body's ability to fight cancer, being near these power lines. That was the theory. Now, just to jump to the end, it's been, I think, the consensus now is that the correlation between living near the power lines and getting leukemia was not caused by the power lines. It's just other things that children who live near power lines maybe are also exposed to actual bad things. But back in the 80s, this was not well understood, so it was a valuable kind of alley for science to drive down to try to understand this. So some researchers made an experiment where they killed some chickens. And they take the chicken brain and divide it in 2 halves. They measure the calcium flowing out of the chicken brain. So apparently calcium channels are like a thing. Okay? And for each Yeah, I know. I'm trying to like talk like my kids, you know. Like I was writing something the other day, and I actually like non-ironically used the phrase "my dude," which is like what my kid says all the time, and it really worked. So you can stay young. I'm telling you, it's possible. So they divided the chicken brain into two parts, measuring the calcium efflux. One half of the chicken brain gets the control treatment, which is just whatever, just sitting there. The other is in another room exposed to low-frequency magnetic fields. And they did a series of 38 experiments, starting at 1 hertz, then 15 hertz, 30 hertz, 45, stepping up every 15 hertz until 510 hertz. So at every frequency, they did an experiment with a bunch of chickens, and they had the exposed and the control. And you can take the difference and estimate the effect of the exposure on calcium efflux. Well, they did something else to be safe. They also did a sham experiment. The exact same, except the whole thing was turned off. So like the exposed, there was no exposure. And what they actually did was they did treatment minus control in the exposed group, and then they did treatment minus control in the sham group, and then took the difference between them. Completely safe. So they did this result. They got some results, kind of equivocal results. They found some statistically significant patterns at different frequencies, more than you would expect just by chance. Like taking their data at face value, there was something going on. Nothing going on in the sham data, though. If you look at the sham data, they're completely consistent with 0. Okay, which, by the way, I'm doing a hypothesis test. It has its value here, that 0 is consistent with the data. So here's a question. There's two possible analyses. The one is the safe analysis, which is take treatment minus control, subtract expose minus control, subtract sham minus control. Right? That's safe, just in case you're controlling. Okay, if there's some bias that's snuck in, you're subtracting it. The other analysis is just take expose minus control. Throw out, well, why throw out the sham? Because by subtracting sham, well, you're doubling your variance, right? So there's a cost to including that. So it's similar to our other puzzle. Like, what's the right thing to do? And we looked at the data. We took advantage of the fact that there were 38 experiments, so we could see that there wasn't much going on, and there's no evidence for anything going on in the sham. So you have to think, like, which would you do? 30 seconds. With your neighbor, what would you do? Would you subtract the sham or not?
Okay. Stop.
So I'll tell you the answer. Okay. The answer is you should not use the sham data. You should throw away the sham data. Now, I won't say you should act as if the sham data were never collected, because the sham data contain the elements of their own destruction. It was only through seeing the sham data, right? So this is like, you have a business and you hire 2 accountants just to make sure nothing got messed up. They give you the same answer. It doesn't mean it was a mistake to hire 2 accountants. Okay. Well, maybe it was a mistake for them to do 38 sham experiments. Because if you read their paper, and then a few years later they wrote a follow-up paper, they said that there was some uncertainty in their results, and they just didn't have the budget to go further. So in fact, if you look carefully at what they did, they doubled their cost. Well, they doubled their cost because they had fixed costs, but they doubled their variable costs, right? They could have gathered twice as many data points for that, right? And then by including the sham data, they doubled their variance, right? So they paid twice for that. And that is actually serious. I mean, then it's like, to the extent the experiment was worth doing in the first place, they were hurting themselves twice. Now, but this the fact that I told you these two stories is interesting. I could tell you more. I don't know if I have time to tell more stories, but for these two, is that superficially, like, they're very similar stories, and the superficial message is the opposite, right? From the first story, the message is, do the conservative thing. It turns out it's just as efficient. The second one is, don't do the thing that looks conservative. It's throwing away information. Now, this is one of the frustrating things about statistics to students, and I think those of you who do like analytics will realize this is confusing to people you talk with, is that the answer often seems to depend on something technical. And when people try to kind of jump to the solution, it seems like they're often like they're often like generalizing at the wrong point, right? Like you'd hear the first story and you'd say, well, the message is, you know, do the safe thing. And then you hear the second story and it seems like a different message. So it really is a challenge. And it's easy to get fooled. And when we teach, it's like that. Like we say, oh, this, you really have to worry about X, Y, and Z. But then here, don't worry about that. That's, you know, this is just a rule of thumb we can use. And people get confused. When I was a student, my advisor in the class told us that if you have a randomized experiment, it doesn't matter if the people in the experiment are a representative sample of the population. Because you have a randomized experiment, so you get kosher inference for the treatment effect. But that was wrong if there's any treatment interaction. Because if the treatment interacts, it's bigger for some people than others. Then if you've estimated the treatment effect in an irrelevant or non-representative sample, that can be a big problem, right? So there's a lot of, like, there are these principles. It's very confusing. So how do I try to resolve these problems myself? I try to use multi-level modeling. And that's kind of the statistics or math version of the simulate the world thing that I told you earlier. So in this case, let's do it in these two examples. Okay. So first, the 4 treatments with the 5 dishes and the 6 things. So I can set up a model, and I can say, well, let's just start with an additive model. There's treatment effects, there's dish effects. You work it through, you see what happens. You can try different estimators, and that one is kind of easy to do. You kind of work it out, and it turns out that taking the average of the 5 for each one is close to optimal. Now, if you're really careful, if you do the full Bayes, you stand, then you do that, and then you get a little better, because you can get a slightly better estimate of the variance. You can even model the variances varying. There's a little more that you can get out of it, but not a lot. And you can see that by simulating the fake world. Now, in my second example of the chickens, well, I need a lot here. Okay, so what's the model? So the model is that there are 38 effects that I care about. That's what I want to study. The effect at 1 hertz, the effect at 15, the effect at 30, so forth. That's what we care about. But then, okay, you have to kind of like reverse engineer what people did to figure out what their model was, right? So if these people were doing a sham experiment, assuming they're not like, let's give them credit for kind of knowing what they're doing, even if they didn't analyze the data right, and say they were concerned there could be a separate bias at each frequency. Because if it was a constant bias, you would need to do 38. So we have to model there being 38 treatment effects and then 38 biases. And then from there, it's not hard to come up with a model where the outcome for the sham experiment is bias plus noise. The outcome for the exposed is treatment effect plus bias plus noise. And then you see you take a difference, and the bias drops out, and it's so simple, cool, but you find there's an advantage to simplicity, but you do the full Bayes thing, and it turns out that you can do partial pooling with the amount having to do with how variable the sham results are, and you can get a better answer. So we can work it out and figure it out. So that's kind of what we have to do. That's how we have to solve, just like probability problems the same way. We have to solve them by creating the fake world. I don't think there's any other way of doing it. Now, when I do that, I'm putting myself on the line, right? Because you can come back and say, I don't believe your model, okay? But that's fine. I want that. I don't want to come up with a method and then you say, I don't believe your method. I want to model, and then you say, I don't believe your model, and then we can do better. So, you know, I think getting back to all those p-values, sometimes I think that if all those bozos would just stop using formal statistics entirely, that would be fine with me. Just present your results. I did this study with 40 college students, and this is what I found. Put me on NPR, whatever. Give me a goddamn TED Talk. That's fine with me. Let's be open. Okay. But why do it? Why bring in statistics at all? Okay. That's how I feel. But the funny thing is, from their perspective, they just want to do their science, and people make them do this horrible statistics. They make them do that even though they don't want to. And so I'll just conclude my talk with this, that we've got a ways to go.
Do you want to do questions?
What?
Do you want to do questions?
Tell you what, we're going to break the rule, especially for Dr. Gelman. We'll take 3 questions.
Sure, if anyone has 3 questions, that's fine.
We have time for 3 questions. All right, who has a question? Can we get the microphone, actually? Kaz, can you grab the microphone really quickly? Anyone have a question? Now's your chance. Only questions allowed the whole conference. All right, there we go. The microphone is going to be hard to get to. Let's grab this.
Thank you for your presentation. So, for example, I want to predict something using many variables, and kind of I want to use the hierarchical modeling because there is natural cluster within my data set. But now how I design the hierarchical model and how can I do the variable selection?
Oh, you can, I mean, there are different approaches, but I would throw all of your variables into your model. And then I would partially pool them. I would use information at the level of the variables themselves. So the simplest thing to do would be if you have a bunch of variables and some you think more important than others, then you can label them as like 1s, 2s, and 3s, and then have prior variances that are larger on the 1s and smaller on the 2s and still smaller on the 3s in order to do more partial pooling for that. We also have techniques using leave one out cross-validation where you can try to improve things in different ways. It's really hard to answer. To just answer in general, I mean, it's kind of impossible, but let me say there is a principle in statistics that the most important thing about a statistical method is not, the most important thing is not how you analyze the data, but what data you include. And the most important thing about a statistical method is not what it does with the data, but to what extent it allows you to include more information.
Thank you.
Cool. Okay, we have the mic right over here. Wait, just pass it forward.
Thank you very much. So you advise us to simulate the data, and you also admit that it's very, very hard. I agree. I just don't know how to start with that. I've tried, and I stare at a blank piece of paper, and it is hard. Do you have any advice for a novice trying to learn this? Maybe books or approaches or something that I could get better at that skill set?
I would say, well, you know, we are like trying to write books and all that with this exam. I mean, I think we're only recently have we realized the importance of fake data simulation. So like we're putting some examples in Regression and other stories and things like that. But I would say in a given example, just start simple. But I think the paradox is you need to start simple, but sometimes it's only through the complexity that you'll learn things. Like the example that I just told you about with the chickens, there's 38 experiments. If you did it with just one experiment, you wouldn't be able to get anywhere. So it is a bit like, you know, like building a house. Like you put up one wall at a time, but the walls don't hold up until they're all there and the roof is there too. So it's kind of a little bit of a commitment, I'd say.
All right, last one over that way. Kaz, can you grab the mic?
So this is also about simulating the data. If you're assuming a full probability model when you're doing that, because that sounds like what you're doing, why not just take a straight full Bayesian approach. And if you're saying, I don't know what the probability generating model is, why not just do something frequentist like a bootstrap? Like, what is the advantage of simulating before if you really believe that this is the true distribution?
Oh, I've never believed that the true model at all. So that's an easy one. So I would say that I will set up it's like I'll set up a probability model that's can kind of reproduce something that seems sort of close to reality, and then once that model is there, I can try different competing approaches.
But
so sorry, yeah.
I was going to say, but how do you know it's close to reality until you have the data?
Well, you know, I don't, and even after I have the data, I don't really know. But like, it's often they're just minimal things that you need. So like, if the modeling, like I said, the modeling included the experiments included sham treatments, so it makes sense to put that in. Or in this like A/B test thing, the very fact that you have to say, well, how big are the effects? How fast are they coming in? Like, just asking the questions is often, I think, the most valuable part of it. And yeah, it won't be the most realistic thing, but I think it'll be a lot more realistic than like trying to pull out formulas from some book on bandits or whatever. You know?
All right, with that, thank you very much.